Welcome back to Neural Networks for Architects, day 3 on numbers and things. In the previous chapters we talked about how to picture reality by numbers and taking different perspectives, and how to use numbers to have certain glasses on what's going on there on planet Earth. And now if you collect all these numbers, you have a key problem in curating this data and getting control of a huge amount of data. So we're talking about 10,000, 100,000, a million of vectors and pictures and so on, and how to work with that. This is the problem we want to address in this chapter. So let's have a look. So how to start. This is the first chapter here, the first episode. This is just episodes, and this is not it's not a logical line. It's just episodes. Go in if you're interested, skip it if you don't need it. So, for example, if you want to go for key points in floor plans, this is working like this. So you have these two floor plans. Now we make a, so these are, imagine you have 10,000. Now we say key points, and our data set now is, first is the input of a neural network. These is the output. These should be the key points. So, and you start simply saying this is now the center point of it. Now what I've written here is, and you can look it up with all the documentation, how it is done. I make an editor and a simple interface. So this is the first one. We have the first and the point. So what we can now do is we can put it to the key point here. We can add another one, put it here, add here, add here. Then we save it. And if we now go for, this is with data set. Set with S. Then you see the 4 key points here. So now this is proper. Now we go to the second one, and then we are here. We put it here. We add. So we also can delete, save. We can go back, plus. Look it up if you're interested how I did. I think these are the key components how to do. What is more important is that you start, for example, with 100 of these floor plans. You make all the key points. You say this is what AI should deliver with a new floor plan. You simply say that. And then you have to do it for 100 times. Then you start a neural network training with these 100 examples. Then you get with another 900 of these examples, or 500. So, and run the neural networks to do the job. So this neural network will then make mistakes. For example, it will come then with these things here, put it here. It will deliver certain things, but you're not happy with it, so it will be not accurate, and so on. Then you go there, and you have to correct that, the 1000, but it's much less work than with the first. You save it, and then you have a bunch of 1000 good examples. So the neural network with very few examples will make, for example, 60% correct, 40% you have to correct, delete, add, and so on, and then you make good examples of it. But it's getting faster. Training the neural network again with these 1,000 good examples, and it will get better results. For example, 80% accuracy. Train another 5,000, bam, 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 and by that you can grow. So, and keep these circles running. This is what all social media are doing. They're always saying, if people do something, thank you, now I know better. And keep these loops running. And this is the way, look how Event Handler used it and did it, how this is, can be implemented, and which tools in Mathematica are good for that to speed up this process of increasingly improving neural networks and by building more and more larger data sets by hand. So this is the idea how to come to data with the support of AI, your AI. So then it's very interesting that this stuff here, you can use AI embedded in Mathematica. So because it's so expensive to have all data accurate, you can't say I don't know, and it doesn't matter because there is these kind, you can synthesize missing values. So it's self-explaining and it just fills it, and that's good. So keep in mind that you don't have to, because it's expensive to make to get everything from everything in all aspects. You don't need to. It's much better to get everything and not to be too accurate. So, or what you can do is very interesting as well. You even don't have to measure anything. You just take examples of collections of data, and you can fill the missing ones, and then you fill that with into a feature space. Let's go look how it works. So, and then you have a feature extractor, and you directly get a vector for that. And this is always consistent, and you fill and you color and you temper a space like a picture or a sound, just with data. So these are, for example, with these 4, just to get the idea, with these 4, these are the 4 points in a 3-dimensional space, and it looks like this. So these are the 4 points. So 3, 4, filling and spanning and tempering the space. You can do the same, just to show you how this works, with sentences of a book. So you temper a space with sentences of a book. So let's look how this works. There's Alice in Wonderland of Carroll. We get all the sentences, we ask how many sentences are there, and get a feature extractor for these sentences. So it's 550 sentences and 547-dimensional space, which means these are all the points of the sentences. So we take this feature extractor to all the sentences and get the points for all. That's very fast. All the sentences. Now vecs are vecs of 1. So it's a 500. It's 47 dimensions. Or let's look at dimensions of vecs. So yeah, it's like a picture. So that's our feature space. Now you can ask, very, very interesting. So you can ask any kind of question. Why is the door locked? You get a point in this feature space tempered by the book. The sentences of the book, and you get a point with any kind of question. So this is vec. So now you can ask, what is the nearest neighbor of this question within the book? And he says it's sentence number 30, and here this is the sentence. There were doors all around the hall, but they were all locked. And you see, it works. It's a neighborhood. So you have a 500-dimensional space. You locate all the sentences, and depending on their difference, and you make a most contrast to this space. And just with Euclidean distance, then you can find interesting neighbors. So, or let's make it in one step. So, for example, Alice has nothing to do with it. Yeah, probability density of normal distribution with quantity and so on, some probabilistic, stochastic thing. Ask what Alice is doing. By this time, Alice had found her way into the tiny little room where a table, whatever. So it's working on anything. And that's the alien word. So we didn't understand anything, but we pictured the world in a certain, and tempered it with the differences, and that then it resonates to anything. And it's not too nonsense. That's very interesting as well. A certain character then. So if you have that, for example, what is a little puzzling is these 540 dimensions. Now we can do a dimensional reduction. So take these vectors of 547 dimensions and reduce it to 16. So, and this is a reduction function. So let's do it step by step. So now we reduce it to, we put in 400, and we keep, it's like getting down with resolutions of images. So we go down with the resolution of dimensions to 16, and we have, of course we lose contrast, but now we can reduce all the vectors. So we have 500 sentences from a vector of 550 to a vector of 16. So we have that, and we can ask now our feature extractor, we reduce it to 16 and ask what is the vector, so the point in the 16-dimensional space, and we ask for the friends and the neighbors as we did before, and he still finds sentence number 30. So it just still works, but it's much cheaper. So if you go to true, you can make a rendering to all these 550 sentences. You have the rendering, I have the tooltip. So these are extreme. They're just hush, it's not a sentence. Nobody moved. Where are you? These are all the sentences. This is done with tooltip. So you can analyze these things if you like. So, but just as an example, if I ask now the two-dimensional space here in the neighborhood here, and ask there where is my why is my door locked, then it makes nonsense. It's not enough resolution. Yeah, 16 was good. Of course, the 500 is good, but expensive. But the 2 is definitely not contrast enough. But you can see how the space is filled. Now, there are extreme values. In most cases, these are errors. And so, for example, if you do measurements and you have these extremes, then there are mistakes, some errors. You simply get rid of that. That's the next chapter. If you get rid of the exceptional values, this is done like this. So, let's go. just continue with the 2 dimensions. Vector is vector 2, vex is vector 2. Now we say we want to exclude 4% of the, no, 2% of the values, so the 2 extreme values. So, and then we have this range in x and in y, where 98% of the points are in and the others are out. So then I have some helper functions. It's called extreme value q, and then we can ask the exceptionals. These are the 2% of numbers which are not in the range of the normal. So these are extreme values. Here, these extremes. These are the numbers. And then we can ask exceptionals, flatten sentence of this as a column, rendered as a column. Here, hash, all this is there. These are very exceptional sentences, decreasing the resolution of the, or disturbing the resolution of the majority of sentences. So now I can go with the graphics for the center of the things, and you see then it's not so much disturbed with the extreme values. So, but nevertheless, still, for example, now in x and in y, there is a different resolution, and this is the next thing. So if you go with Euclidean distance, then here the x and the y have a different importance. And to normalize that, this is a principal function. Here you see, for example, this is an extreme example. You have in x, it's very low level and low numbers, and in y, it's always 10 times more. So if you make Euclidean distance, then the y is out, it gets more weight than the x. And to put that into the same proportion, you just take the feature extraction with standardized and extracted features, and then you see now they're playing in the same range, but they keep their differences. So doing that with ours, so we delete the extreme values. This is called now vex n. We have the graphics of vex n, and now we do the graphics. We do the feature extraction, standardized feature extraction. Instead of vex n, we have the points of vex n extracted, standardized, and the rest is the same. And here we see it's spread, getting more contrast, which is important to as an alien, to have proper contrast and proper balances of whatever you're doing. Good. This is what I wanted to show. A sequence of episodes around huge data sets and how to manage things. Next will be on the technical implementations, the tools Mathematica provides for numbers and things. Thanks for watching. See you in the next chapter.